In the last video, we saw some of the drawbacks to Euler's method. So we would like to make some improvements to Euler's method in order to improve the accuracy of our approximation. Now, the first step in Euler's method is given by the initial point y0 plus the slope f of t0, y0 times delta t. What we would like to do is improve our estimate by, instead of using one slope at t0, y0, using the average of two slopes. So that first slope will still be f of t0, y0. And so if I look at this plot below, Euler's method was saying we should follow the slope of the tangent line to delta t, noticing that we're going to incur an error, that we're going to overshoot our solution to the differential equation by the time we get to t0 plus delta t. So because we're going to overshoot the solution, my proposal is that we also consider the slope at the end of the time interval. Let's consider the slope also at this estimated value for our solution at the end of the time interval. So essentially, we're going to reevaluate the slope here at the end of our time interval. And we're going to look at the slope field and notice that the slope there is much shallower. So my proposal is that we evaluate the slope at t0 plus delta t, and our estimated point for the solution using Euler's method. And our estimated point was y0 plus s1, our first slope, times delta t. So what we've done is we have evaluated the slope here at t0 plus delta t and y0 plus s1 delta t. So now what we can do is, in order to take one step in our new improved Euler's method, is we can average the slope from the beginning of the time step, which is given by that blue slope, and the slope, the estimated slope, from the end of the time step, which is given by that green slope, so that we can start at our initial point, y0. We can take the average of the two slopes, so s1 plus s2 over 2, and then we can multiply that by delta t. So what that looks like is I will consider an average of the two slopes. So this purple slope is going to be an average of the two slopes that we found, okay? And what that does is that gives us a better estimate at t0 plus delta t, which is given by y0 plus s1 plus s2 over 2 delta t. And this is called an improved Euler's method. It also has the name that it is a second order So it's a second order Runge Kutta method. So this method was developed by two German mathematicians, Runge and Kutta. It's called a second order Runge Kutta method because the error in this method is proportional to delta t squared. Now, something I didn't mention in the last video is that the error for Euler's method is proportional to delta t. our time step size. That meant that if we cut our time step in half, then that was going to cut the error in half. Well, in this case, our error is proportional to delta t squared. So that means that if we divide our time step by 2, that'll actually cut our error by a factor of 4. Okay, so let's do the example that we did before with Euler's method. Let's do y prime equals negative 2y plus 5t, where y of 0 is 5. And what we're going to do is we're going to take 2 steps of the second order Runge Kutta method. Okay, so we're going to start with the 0th step, where time is starting at 0 and our y is initially 5. And then we want to take 2 steps. Okay, so the delta t in that case is 1. So we're going to move from time step 0 to 1, and then again to time step 2. Okay, so we're going to compute our first slope using Euler's method. Okay, so that's going to be simply negative 2 times our y, which is 5, plus 5 times our time, which is 0. And so we're going to get an initial slope of negative 10. And we saw before what that did is that took our solution and it moved it down very, very quickly. So instead of just using that one slope, we're going to average 2 slopes. So let's find the second slope. So that's going to be negative 2 times, we're going to take our y value of 5, but now we're going to add S1 times delta t. So S1 times delta t is going to be a negative 10 times 1. And then we're going to add to this 5 times, and then t plus delta t. So t is 0 and delta t is 1. If we add all of that together, we're going to get a positive slope of 15. Okay, so now what we're going to do is we're going to average the 2 slopes. So we're going to do negative 10 plus 15 over 2 times our delta t of 1, and that's going to give us 2.5. So we take the average slopes times delta t, which is 2.5, we add it to y, and in fact, we're going to get 7.5. So now we're going to repeat this process. So we need to come up with the new slope, S1. Okay, so our new slope is going to be our negative 2 times our y. Our y in this case is going to be 7.5. And then we're going to add to it 5 times 1. So that's actually going to give us a negative 15 plus 5. So that's a negative 10. So again, we get a first slope as negative 10. Our second slope is going to be negative 2 times, okay, our y sub k is 7.5. And then we're going to subtract S1 times delta t, so 10 times 1. And then we're going to add 5 times 1 plus 1. So that's t plus delta t. By doing that, we're going to get a negative 5 plus 10. So let's see, we're going to get, I'm going to do a side computation here. So negative 2 times 7.5 minus 10. So that's times a negative 2.5 plus 5 times 2. So that's going to be negative 5. Oh, it's actually going to be positive 5 plus 10 is going to give you 15. Okay. Okay, so again, we're averaging the slopes negative 10 and 15. Multiplying that by delta t, we're getting a negative, or 2.5. And then so y sub k plus the average slope times delta t, it is going to be 7.5 plus 2.5, which gives you a total of 10. Okay, so our estimate based on the second order Runge-Kutta method is going to be 10. Now that estimate isn't going to be very accurate. In fact, I think it ended up being the same estimate that we got for Euler's method, but this will converge much faster to the solution as we increase the number of time steps or decrease delta t. So let's look at what this method looks like in slopes. Okay, so I have my equation y prime equals negative 2y plus 5t. We saw Euler's method, right? Initially, if we were using 5 steps, we were able to build the solution. I want you to notice that the dramatic drop on that first time step, okay? But also it does have that general shape to the solution of the differential equation. Okay, so what does the second order Runge-Kutta look like if I take 5 steps? Well, here, notice that I have an orange arrow, and that's the average of the two slopes, the slope at the beginning and the end of the time step. Okay, so we're averaging a slope that's negative, actually, with a 0 slope. Okay, and that's going to give us the red slope. Okay. And so what we're going to do is going to build solutions based on the averages of the two slope. So here we go. We're going to add the next term, and then we're going to add the next slope, and then the next slope, and then finally the last slope. And what you can see is we've built a new solution to the differential equation, and it doesn't quite have that same dramatic drop that the solution to the solution using Euler's method had, okay? In fact, if I increase n, then you can see that the true solution also doesn't have that dramatic drop, okay? So if I use a better estimate here, the true solution doesn't quite have the same dramatic drop that Euler's method had. So the second order Runge-Kutta is a better approximation in this case.